Hello everyone, my name is Prince Raj Yadav. I'm final year BTech Engineering Physics student at IIT Roorkee, and this is my presentation for the course PHN 631 Nuclear Instrumentation. The topic of my presentation is dead time determination method for gamma ray detectors using attenuation law. So in this presentation, I'm going to talk about the dead time of any instrument. Basically, I'm going to stick to detectors, dead time of detectors. The factors affecting dead time, correction models or correction methods, the previous dead time determination methods, and the dead time, very topic of my presentation, dead time measurement using radiation attenuation law. Then I'm going to talk about an experiment which was done to verify DMRAL, and at last the conclusion of this presentation. So starting off with the very definition of dead time. A minimum separation time is required for two radiation events to be recorded in radiation detectors. This separation time is called the dead time of a detection system. There are two factors which affect the overall detection system dead time. First one is detector's intrinsic, which depends on geometry, materials, and design of the detector, as well as operating conditions such as applied voltage and temperature. The second one is pulse processing dead time, which also includes the MCA dead time. Uh, the pulse processing dead time is associated with the electronic circuitry of the detection system. Now, there are two simple generalized dead time correction models. One is paralyzed and the other one is non-paralyzed. The paralyzable correction model assumes that if radiation interaction occurs within the dead time of the detection system, that radiation interaction is not recorded as an individual, but will reset dead time, hence extending the dead time. The parallelizable correction model is mathematically expressed as m is equal to n into e to the power minus n tau, where m is the observed count rate, n is the true count rate, and tau is the dead time of detection system. Next is non-parallelizable model. The dead time for a detection system is fixed. An interaction that occur during this dead time that is not recorded as event, but after the initial event is recorded by the detector, the non-paralyzing model allows the system to recover after a fixed dead time. The mathematical model is represented as m is equal to n by 1 plus n tau, where m, n, and tau are observed count rate, two count rate, and dead time respectively. But it is important to emphasize that no detector in reality follows any of these two correction models, but they fall into in between of these two detection models. For example, these were the two hybrid models developed which gave more than 90%, 95% accuracy. I'm going to talk about the determination methods which were used previously. One of the most common methods for determining the dead time of a detection system is the two source model. It is commonly used model to estimate the dead time of a gas filled detection system. The method can be implemented simply by obtaining the radiation rate for two sources, both individually and in combination. Now, the second common dead time determination method for a detection system is decaying source method. This method can be applied according to the known exponential decay behavior, which is as n equal to n naught e to the power minus lambda t plus nb, where nb is the background count rate and lambda is the decay constant of the isotope. But this decaying source method is only feasible for isotopes with short half-lives. Next, I'm going to talk about DMRAL, in which we are going to use attenuation law, which is I1 is equal to I naught e to the power minus mu x, and everything I'm going to explain on the board. So now I'm going to derive the DMRL mathematical expression. First of all, as we know, if there is an absorber of thickness x and attenuation constant mu, and light of intensity I naught is emitted on this absorber, then we get transmitted light as of intensity IT, which can be expressed as I naught into e to the power minus mu x. And this we are going to use this in this DMRL method. So the setup for this DMRL daytime determination method is we have a detector D naught, a source, and an absorber of thickness x, and again a detector D1. This source will emit N naught radiations, and after this absorber will get N1, and this detector D1 will count M1 rate of this radiation, and similarly this D0 will count M0. So for non-paralyzable model we know that M0 is equal to N0 plus by 1 plus N0 tau, and this M1 would be similarly M1 would be M1 is equal to N1 by 1 plus N1 tau. And we know that from attenuation law that M1 N1 is equal to N0 into e to the power minus mu x, which can be rewritten as N0 into e to the power minus mu by rho x rho, where this mu by rho is mass attenuation constant. So after substituting this into this, we'll get now we have a new expression for M1 and an expression for M0. Now we are going to take ratio of these two, M0 and M1. And from this we can calculate the value of N0 tau, which can be which would be N0 tau is equal to M1 e to the power minus mu by rho x rho minus M0 whole divided by M0 minus M1 into e to the power minus of attenuation constant x rho. So this would be the value of, as we know, M0 will be the rate detected by D0, M1 would be the rate detected by D1, and these mass attenuation constant, thickness, and the density of this material would be known as they are the properties of this material. So the value of N0 tau can be determined by this equation, and by using this N0 tau in the expression of M0, we can find the value of N0, and again by using the value of N0 we can calculate the value of tau. Here tau is the non-paralyzable model dead time. So in this way we can determine the non-paralyzable dead time model of. Now similarly, I am going to derive the expression for paralyzable dead time model. In this again, we are going to have a detector D0, which will count M0, a source which will emit N0, an observer of thickness x and density rho. After passing through, we'll get N1. A detector D1 will detect M1. This time, paralyzable model. Now, since we know that for paralyzable model we have M0 is equal to n naught e to the power minus n naught tau, and similarly m1 would be n1 e to the power minus n1 tau, and this n1 we can write it as n1 is equal to n naught e to the power minus mu x, which can be written as n naught e to the power minus mu by rho, which will be again mass attenuation constant into rho x. By substituting the value of n1 in this equation, we'll get m1 is equal to n naught e to the power minus mu by rho x into e to the power minus n naught e to the power minus into rho x tau. Again, we are going to take the ratio of m naught and m1. We'll get and from this we'll get n naught tau is equal to ln m naught by m1 minus mu by rho into rho x whole divided by e to the power minus mu by rho into x rho minus 1, and this will be our expression for n naught tau. From this, as we know, m naught, which is the counted by d naught, m1, which is counted by d1, and mass attenuation constant, density, and thickness are known for this absorber. From this, we can find the value of n naught tau, and by using the value of n naught tau in this equation, we can find the value of n naught, and again by using this n naught, we can find the value of tau, and this tau is the parallelizable model delta. So now I'm going to talk about the experiment which was carried out at Marmara University Nuclear Physics Laboratory, in which sodium iodide thallium doped scintillator and 137 cesium radioactive gamma source were used to find the dead time of the detection system. And this experiment was carried out on December 1st, 2018. In this experiment, polyethylene and lead were used as absorbing materials in the experiment by individually placing them between the detector and the radioactive source. So the and all the readings were taken for 5 minutes, and these were the readings recorded when there was no absorber in between source and the detector. And this was the readings recorded when lead was used as an absorber in between source and the detector, and again this was the reading recorded when polyethylene was used as absorber. After conducting all those mathematical equations and calculations, these were the recorded dead time. For non-paralyzing dead time, we and lead we got 8.39 microseconds. That for polyethylene we got 19.02, and in paralyzing dead time we got 8.35 for lead and 18.79 for polyethylene. So the dead time difference between these two models, non-paralyzing and paralyzing, for a specific absorber is not much, but that of between lead and polyethylene for a different absorber, we can see a drastic change. This was because the mass attenuation constant was taken from the literatures, and that was not mentioned. That was not mentioned in by the manufacturer. So that was the problem for this anomaly. But the values were very close to ideal values, which we used to get from decaying source method and two source methods. Coming to the conclusion of this PPT, the two source method is one of the traditional method to determine the dead time of the radiation measurement system using two similar radioactive sources, in which we count the rate by one of the source, then in combination of the sources. The decaying source time determination method can only be used when there are radiation sources with sufficient short half lives. And the reason why polyethylene dead time values are 2 times higher than those of the lead is attributed to the fact that the mass attenuation coefficient are taken from the literature and they are not provided by the manufacturer. The shape symmetry presents between the shielded and unshielded photopeak confirms that the buildup factor can be neglected in the dead time calculation for the thin shield. And this buildup factor plays a role when we take a thick absorber. But in this experiment, we took a very thin absorber, so the buildup factor was taken as 1. The dead time calculation can also be obtained using linear attenuation coefficient equations instead of mass attenuation constant. So this brings us to the end of this presentation.